This video is intended to look at the class problem that's given on the Moodle site, class problem on first order sediment load estimation. And this is a really simple technique. It's not as accurate, of course, as other methods that we're going to be looking at, but it would be a way of estimating sediment load if all you had was sample values of sediment concentration and discharge at the time of sampling without actually having a continuous record of flow. So what we're going to do is to look here at the files that are given in here. I'll open this up and we'll see that there are three files. One is the class problem description, and then there are two Excel files, one with data and the other one is the data with the solution. So we'll open up the Word file. Basically what we're given here are sample data for flow and TSS for the Lower Canyon River. They're contained in this Excel spreadsheet, and data span over the period of time from March 2007 to June 2012. Here, the first thing we're going to do is to estimate the mean annual sediment load in metric tons per year using this flow and sediment concentration data that are given in the Excel spreadsheet. The daily flow for any given day of record is just the flow multiplied by the sediment concentration, and one needs to convert the units. In the case here, if we're going to do metric tons per year, the conversion unit is 0.002449 if your discharge is in cubic feet per second and your sediment concentration is in milligrams per liter. We will be taking the daily load values and then average them and multiply by 365 to get the estimate of the annual value. I might have misspoken there. I think this conversion factor is to convert to metric tons per day, and then we multiply by 365 to get metric tons per year. And then we're going to estimate the annual sediment load for any given year and plot that. Okay, so as I mentioned, the files are here. You go to the first Excel spreadsheet or go to the second one, and I'll go to the second one because it's got the results in it. So this is what the Excel spreadsheet looks like if you were to open up the first one. It's got the date of the sample, the discharge on the date of the sample, and the TSS in milligrams per liter. And then we've calculated here the load using this discharge, this concentration with the conversion factor to give metric tons per day. If you don't remember, a metric ton is 1.1 times an English ton. An English ton is 2,000 pounds. A metric ton is 2,100 pounds, or 2,200 pounds. Okay. What I've shown on here is that conversion factor. This converts the load to give metric tons per day, and that was mentioned previously. Now, if I take the discharge values and plot them against the TSS values, you can see the kind of relationship that we get. You can see that there's variability in the relationship between TSS and discharge. I've got a trend line fitted to it that goes through the point 0 through the origin of the graph, and the R-squared value is 0.28. It's not all that good, but that's because of all the spread that you see around the best fit line. Now what I've done here is to take these values, metric tons per day, and for each year then calculate the total load associated with that. And the mean load in metric tons per day is 309 for this first year, 2007. The metric ton load per year is given by this purple, which is 112,867, and that's for the year 2007. I did it for 2008, get 90,000. For 2009, we got 367, quite a bit smaller. 2010, 2,977. For 2011, it's 117,000. And then 2012, there's only a partial record, and that one over that partial record gives us pretty high value, 382,000, much higher than any of the other values. So the calculation of the load was done very easily here just by multiplying discharge times the concentration. These are just on the dates of when samples were taken. So we've not accounted for all the other dates in the record when there might have been flow and the sediment that might have been getting carried by that flow. And that's what our analysis with the flow duration curve will help out with, because with the flow duration curve, we will know what fraction of the time a certain flow occurs. And if we have a relationship between TSS and discharge, we can estimate on dates when we're not sampling as to what the concentration is and calculate a load for those values. So using a full flow duration curve will give us a much better estimate of the total load that's coming out of the watershed. If we had a complete record of discharge and TSS, that is, if every day I had a TSS value and a discharge value, that is the best way of estimating load, because then you'd have a value for every day. There wouldn't be any gaps in the data, and you'd be able to get a very good estimate of the relationship between flow and discharge. But because of budgets, you can't do sampling at that kind of a rate. All right, so here, the second part of the, well, before I finish that, or go to that, I should talk about the average. So we had the variability in the annual load. The mean annual load is 102,308, based on the numbers that we got for each year. And the estimate will be using a flux model later. Using the flux model to estimate the load, it gets a value of 95,800 using method 1, which is essentially using the same procedure which I just showed here. So I'm not sure why there's a variation or a difference between them. They're fairly close, but I'm not clear on why we get this difference between 102 and 95,800. Okay. Looking at the second part of the problem was the class problem, wanted to plot the variation in annual load, and so that's what this is for each of the years. I've plotted from 2007 through 2012, and this is a logarithmic scale, so you can see that this one's 382,000, and this one here is 112,000, and it's as low as 367 in the data set. So you can see that there's a big variation in sediment load coming out of the watershed based on the data that we're looking at here.